Most people think they understand the solar system until they try to picture it at the correct scale. That confidence comes from the images we have seen since childhood. The sun in the center, the planets spaced neatly around it, each world large enough to recognize, each orbit comfortably arranged inside a frame that feels almost compact. Those diagrams are useful for showing what exists, but they quietly distort the one thing that matters most here, which is distance. If the solar system were drawn honestly, the planets would shrink into near invisibility and the gaps between them would expand so dramatically that the entire picture would stop looking like a family portrait of worlds and start looking like what it really is. An enormous volume of emptiness with a few scattered objects inside it. The problem is that your brain evolved to understand forests, streets, buildings, and mountains, not tens of millions or billions of kilometers of open space. So when you see a picture of the planets lined up together, your mind accepts it without protest. It feels manageable. It feels local. It feels as if the worlds of our system are somehow neighbors, but they are not neighbors in the ordinary sense. They are isolated bodies separated by distances so extreme that nearly every visual representation you've ever seen has had to cheat just to keep them on the screen. Take a simple model. Put a basketball in the middle of a large room and let it represent the sun. That already feels like a reasonable beginning. Because the sun dominates the solar system in size and mass, now ask where Earth should go. Most people place it somewhere across the room. Maybe on the other side of a table, because that still feels proportionate. In reality, on that scale, Earth would be a tiny bead, only about 2 millimeters wide, and it would sit roughly 26 meters away from the basketball, not across the room. Far beyond the room, you would have to leave the building and keep walking. And if you wanted to place Neptune on that same scale, you would not stop after crossing a hallway or even a parking lot. You would keep going until you were nearly 900 meters away. At that point, the model has stopped feeling like a diagram and started feeling like a landscape. That is what ordinary illustrations hide. They preserve the objects and sacrifice the void. But the void is the main feature. Without it, you do not understand the solar system at all. You just see labeled planets floating in decorative order. The truth is much harsher and much stranger. The planets are tiny compared with the spaces between them. Even the inner solar system, which seems crowded only because we speak of it casually, is dominated by separation. If the planets were actually as close together as they appear in popular graphics, the sky would look completely different. Other worlds would loom huge above us. Their gravity would disturb one another far more dramatically. Collisions and close interactions would be routine. But that is not the system we live in. Look at the night sky and the evidence is already there. Planets do not appear as nearby giants. They appear as points of light. Venus, dazzling as it is, does not hang above you like a neighboring world. Jupiter, although enormous, usually shines as a bright object rather than a visible globe to the naked eye. Even our cosmic surroundings arrive to our eyes as tiny signals because distance strips away the sense of physical closeness. The solar system is large enough that brightness survives where shape does not, and this emptiness is not some minor detail around the edges. It defines everything. It explains why travel between planets is difficult, why spacecraft take months or years to arrive, why even light needs time to cross these distances, and why the solar system feels less like a structure built from worlds and more like a silence interrupted only occasionally by matter. Once that scale settles into your mind, the old textbook pictures stop being harmless simplifications. They begin to look like a very polite lie told to spare you from the real proportions. What surrounds Earth is not a crowded celestial neighborhood. It is a vast cold spread of almost nothing, and that nothing is the largest thing in it. If the scale of the solar system begins to make sense anywhere, it starts with something familiar enough to anchor your intuition. And that means beginning with Earth itself, from the surface, our planet feels enormous, with oceans that stretch beyond the horizon, mountain ranges that take days to cross, and continents separated by distances large enough to shape cultures and histories. Earth measures about 742 kilometers across, a number that seems abstract until you translate it into experience. Walking around the equator at a steady pace would take more than a year, and even traveling non-stop by aircraft would still require hours to cross a single hemisphere. Everything in daily life reinforces the impression that Earth is vast, stable, and dominant, a world large enough to contain everything that matters. But that sense of scale collapses the moment you compare Earth with the first object beyond it. The Moon is the closest natural body to Earth, orbiting at an average distance of roughly 400 kilometers. This number is easy to read and hard to feel. So it helps to think in terms of light. Light moves at about 300,000 kilometers per second, the fastest speed in the universe. And even at that speed, it takes about 3 seconds for light to travel from the Moon to Earth. When you look at the Moon in the night sky, you are seeing it as it existed just over a second ago, which is already enough distance to introduce a measurable delay into reality itself. Human travel makes the gap feel larger. The Apollo missions took about 3 days to reach the Moon, moving faster than any humans had ever traveled before. Modern spacecraft could shorten that journey, but the distance would still dominate the experience because the space between Earth and the Moon is not a small step outward. It is a substantial region of emptiness. That emptiness becomes more striking when you compare it with the sizes of the planets themselves. If you lined up every other major planet in the solar system side by side, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, their combined widths would fit almost perfectly within the distance between Earth and the Moon. The gap between our planet and its satellite is large enough to hold all of them, not as tiny specks, but as full-scale worlds arranged in a single row. This is one of the most revealing comparisons in astronomy because it transforms the Earth-Moon system from something that feels intimate into something that begins to resemble the broader solar system. Even here, in what seems like a close pairing, the dominant feature is separation rather than proximity. The Moon itself reinforces this idea. It appears large in our sky because it is relatively close, yet it is still far enough away that astronauts require days to reach it, and radio signals need time to travel back and forth. The gravitational bond between Earth and the Moon is strong enough to shape tides, stabilize Earth's axial tilt, and influence the evolution of life, but it operates across a distance that dwarfs anything in ordinary human experience. Two worlds interact, not by touching or even by appearing near one another, but by exchanging forces across hundreds of thousands of kilometers of open space. This is the first place where the scale of the solar system stops being theoretical and starts becoming tangible. Earth is large. The Moon is nearby by cosmic standards, and yet the region between them is already vast enough to swallow entire planetary systems of comparison. Once that relationship is clear, the rest of the solar system no longer feels like a collection of close companions. Instead, it begins to look like a series of isolated bodies separated by distances that grow more extreme. The farther outward you move, with the Earth-Moon pair serving as the smallest example of a pattern that repeats again and again, moving outward from Earth, The inner solar system begins to take shape as a region defined not by similarity, but by contrast. These are the terrestrial planets: Mercury, Venus, Earth, and Mars, worlds built primarily from rock and metal, each occupying its own orbit around the sun, each shaped by temperature, gravity, and distance in ways that make them feel less like variations of one design and more like separate experiments. They are grouped together only because they lie relatively close to the sun, yet even here the distances remain immense, and the environments change dramatically from one orbit to the next. Mercury sits closest to the sun at an average distance of about 58 million kilometers, or roughly 39 astronomical units. It is the smallest of the major planets, measuring only about 879 kilometers across, barely larger than Earth's moon. And its proximity to the sun creates extreme conditions that define its character. Mercury rotates slowly, taking about 58 Earth days to complete one rotation, while it orbits the sun in only 88 Earth days, creating a strange rhythm where a single solar day, sunrise to sunrise, lasts about 176 Earth days. Temperatures swing violently between day and night, rising to around 430 degrees Celsius in sunlight and dropping to nearly minus 180 degrees Celsius in darkness. With almost no atmosphere to distribute heat, Mercury becomes a world of sharp transitions, where the surface alternates between blistering heat and deep cold depending on whether it faces the sun. Venus follows at about 72 astronomical units, roughly 108 million kilometers from the sun, and at first glance it appears more familiar. Venus is nearly the same size as Earth, measuring about 95% of Earth's diameter, and for that reason it is often described as Earth's twin. The resemblance, however, ends quickly. Venus is wrapped in a dense atmosphere composed primarily of carbon dioxide, creating a runaway greenhouse effect that traps heat with extraordinary efficiency. Surface temperatures reach about 470 degrees Celsius, hot enough to melt lead, while atmospheric pressure is about 92 times greater than Earth's, equivalent to being nearly a kilometer underwater. Venus also rotates backwards compared to most planets and does so extremely slowly, taking about 243 Earth days to complete one rotation, which is longer than its orbital period of 225 days. The result is a world where time, heat, and atmosphere combine into an environment completely hostile to anything resembling Earth's conditions. Earth occupies the next orbit at 1 astronomical unit, a distance that places it within the region where liquid water can exist on the surface. Compared with Mercury and Venus, Earth appears balanced rather than extreme, with moderate temperatures, a protective atmosphere, and a stable rotation. This stability becomes more striking when viewed alongside its neighbors because the inner solar system does not gradually transition from hot to cold or from harsh to gentle. Instead, each world diverges sharply, shaped by subtle differences in distance and composition that produce radically different outcomes. Mars, at about 152 astronomical units, continues that divergence. It is smaller than Earth, measuring roughly half Earth's diameter, and its weaker gravity struggles to hold a thick atmosphere. As a result, Mars is cold, with an average temperature near minus 63 degrees Celsius, and its thin air offers little protection from radiation. Yet Mars is also a world of enormous geological features. Olympus Mons, the largest volcano in the solar system, rises about 21 kilometers high, while Valles Marineris stretches roughly 0.000 kilometers across the surface. A canyon system so vast it would span an entire continent on Earth. Mars feels both familiar and distant. A rocky planet with recognizable terrain, but shaped by conditions that halted its evolution early. Beyond Mars lies the asteroid belt, often imagined as a crowded field of tumbling rocks. Yet in reality, it is another region dominated by emptiness. The belt stretches roughly from 2 astronomical units, spanning hundreds of millions of kilometers, but the objects within it are widely separated. Even the largest body, Ceres, measures only about 940 kilometers across, and the combined mass of all asteroids is less than that of Earth's moon, rather than the remains of a destroyed planet. The asteroid belt appears to be material that never formed into one, likely disrupted by Jupiter's gravity during the early history of the solar system. Seen together, the inner solar system does not resemble a compact cluster of similar worlds, but a sequence of distinct environments separated by wide gaps where rocky planets occupy isolated paths, and even an entire belt of objects adds more space than substance. Beyond the asteroid belt, the character of the solar system changes abruptly, as if crossing an invisible boundary where scale expands and familiar planetary ideas begin to break down. The rocky worlds give way to giants, composed mostly of gas and ice, bodies so large that comparing them directly with Earth stops feeling intuitive. Distances increase, masses grow dramatically, and the planets themselves transform from solid surfaces into deep atmospheres layered over uncertain interiors. The outer solar system is not just larger, it operates under a different sense of proportion. Jupiter is the first of these giants, orbiting at about 5.2 astronomical units, roughly 778 million kilometers from the Sun. Its diameter measures about 139,820 kilometers, making it more than 11 times wider than Earth. And its volume is so vast that over 1/300 Earths could fit inside. Mass reveals an even more striking dominance. Jupiter contains more than twice the mass of all the other planets combined, effectively shaping the gravitational architecture of the solar system. Unlike the terrestrial planets, Jupiter has no solid surface in the conventional sense. It is composed mostly of hydrogen and helium, with clouds forming layered bands that circle the planet at different speeds. Beneath those clouds, pressure increases steadily, turning gas into dense fluid and possibly compressing hydrogen into metallic form deep within. One of Jupiter's most recognizable features, the Great Red Spot, is a storm that has persisted for at least 4 centuries. Large enough to swallow Earth and still leave space around it, Jupiter rotates rapidly, completing one rotation in just under 10 hours. And this speed causes the planet to bulge at the equator, flattening slightly at the pole. Around it orbits a complex system of moons, including Io, Europa, Ganymede, and Callisto, worlds that themselves resemble miniature planets with volcanic activity, subsurface oceans, and ancient cratered landscapes. Saturn follows at about 5 astronomical units, roughly 4 billion kilometers from the Sun, and although slightly smaller than Jupiter, it remains immense, measuring about 460 kilometers across. Saturn's most striking feature is its ring system, composed of billions of particles of ice and rock orbiting in a thin, extended disk. The rings stretch hundreds of thousands of kilometers outward, yet remain surprisingly thin, in some places only tens of meters thick. Saturn is also less dense than any other planet, composed largely of hydrogen and helium. And if a sufficiently large ocean existed, Saturn would float. Its atmosphere shows banded patterns, similar to Jupiter, though softer in contrast, and at its north pole, a persistent hexagonal cloud structure rotates in place, a geometric feature formed by atmospheric circulation. Saturn's moon, Titan, stands out within its system, larger than Mercury and wrapped in a thick nitrogen atmosphere, with lakes and rivers, not of water, but of liquid methane and ethane, creating a landscape, both alien and structured, farther outward. Uranus orbits at about 2 astronomical units, nearly 9 billion kilometers from the Sun. Uranus is smaller than Jupiter and Saturn, but still large compared to Earth, measuring about 4 times Earth's diameter. Its most unusual feature is its axial tilt of about 98 degrees, causing the planet to rotate essentially on its side. As Uranus travels around the Sun, each pole alternates between decades of continuous sunlight and decades of darkness, producing the most extreme seasonal patterns in the solar system. Uranus is classified as an ice giant rather than a gas giant, composed largely of water, ammonia, and methane in various states. Methane in its atmosphere absorbs red light, giving Uranus its pale blue color, and beneath the clouds lies an interior that may include layers of high-pressure fluid and a relatively small rocky core. Neptune lies farther still at about 30 astronomical units, roughly 5 billion kilometers from the Sun, completing one orbit every 165 Earth years. Slightly smaller than Uranus, Neptune appears more dynamic, with deep blue coloration and atmospheric activity driven by internal heat. Winds on Neptune reach speeds over 2,000 kilometers per hour, the fastest measured in the solar system, and storm systems form and dissipate across its atmosphere. Despite receiving far less sunlight than the inner planets, Neptune radiates more energy than it absorbs, suggesting heat emerging from its interior. Its largest moon, Triton, travels in a retrograde orbit, indicating it was likely captured, and its surface shows signs of nitrogen geysers and geological activity. Taken together, the giant planets redefine scale, each one surrounded by systems of moons, rings, and atmospheric motion, separated from one another by distances that continue to expand, while the planets themselves grow so large that the rocky worlds of the inner solar system begin to feel comparatively small. Neptune often feels like the outer boundary of the solar system, the last major planet marking the edge of familiar territory. Yet the structure does not end there. Beyond Neptune lies a region where the Sun's influence continues, but the architecture becomes looser, more diffuse, and increasingly difficult to define. This outer domain begins with the Kuiper Belt, a vast ring of icy bodies extending roughly from 30 to about 50 astronomical units. Compared to the inner solar system, the Kuiper Belt is enormous, but like much of space, it is dominated by emptiness. Thousands of objects have been identified, and many more likely exist, yet they are scattered across distances so large that collisions are rare, and the region appears almost vacant despite its population. Pluto is the most familiar member of this belt, orbiting at an average distance of about 5 astronomical units, and taking 248 Earth years to complete one journey around the Sun. With a diameter of roughly 377 kilometers, Pluto is smaller than Earth's moon. Yet it represents a transition between planets and smaller debris. Once considered the 9th planet, Pluto was reclassified as a dwarf planet after astronomers discovered other bodies of comparable size in the same region. This shift did not diminish Pluto's significance, but instead revealed that the outer solar system contains a family of similar worlds rather than a single isolated object. Observations from the New Horizons spacecraft in 2015 transformed Pluto from a distant point into a complex landscape, showing mountains of water, ice, plains of frozen nitrogen, and evidence of internal activity that reshapes its surface despite the cold and distance. Other dwarf planets reinforce this idea. Eris, slightly smaller than Pluto but more massive, travels even farther out, following an elongated orbit that carries it well beyond the main Kuiper belt. Haumea rotates so rapidly that it stretches into an elongated shape, accompanied by moons and even a ring, while Makemake occupies another distant orbit with a surface coated in frozen methane. These objects differ in size, shape, and composition. Yet together they form a population that blurs the distinction between planets and smaller debris. The Kuiper belt is not a clean boundary, but a transitional region where the solar system gradually thins rather than ending abruptly. Beyond this belt lies an even more distant and far less tangible structure. The Oort cloud. Unlike the relatively flat disk of the Kuiper belt, the Oort cloud is thought to form a spherical shell surrounding the solar system in all directions. It may begin around 2,000 astronomical units and extend outward to as far as 100,000 astronomical units. Nearly 2 light years from the Sun. At these distances, the Sun appears only as a bright star, among others, and its gravitational influence becomes weak but still present. The Oort cloud has never been observed directly, yet its existence is inferred from long-period comets that arrive from distant, random directions, suggesting a vast reservoir of icy bodies distributed far beyond the planets. Objects in the Oort cloud are believed to be remnants from the early solar system, scattered outward by gravitational interactions with the giant planets billions of years ago. Some were pushed so far that they now drift at the threshold between solar and interstellar space. Occasionally, passing stars or gravitational disturbances nudge these bodies, sending them inward as comets that briefly illuminate the inner solar system before retreating again into darkness. This process implies that the solar system is not a closed structure, but one that gradually merges with its surroundings. Its outermost components only loosely bound. Seen from this perspective, the solar system does not end with a final planet or a clear edge. It fades outward through scattered ice, distant debris, and eventually into the interstellar medium, where the Sun's gravity gives way to the influence of nearby stars. The transition is gradual, measured not by a boundary, but by diminishing control. And the farther outward the view extends, the more the solar system begins to resemble a region of space rather than a defined structure. Its outer limits dissolving into the larger galaxy that surrounds it. To understand why the solar system looks the way it does, and why Earth ended up as a habitable world rather than another frozen or scorched planet, it helps to step back billions of years to a time before the Sun existed. The solar system began as part of a vast cloud of gas and dust, often called the solar nebula, stretching across light years of space. Something disturbed this cloud, possibly a nearby supernova shockwave or gravitational interaction, and parts of it began to collapse under their own gravity. As the cloud contracted, it started to spin faster, flattening into a rotating disk with most of the material concentrating toward the center. Temperatures and pressures in that central region increased until nuclear fusion ignited, forming the Sun. Around it remained a broad disk of leftover material, and within that disk, the planets began to take shape. The formation of planets did not happen all at once. Tiny grains of dust collided and stuck together, forming larger aggregates that gradually grew into kilometer-scale bodies known as planetesimals. These objects continued colliding, merging, and sometimes breaking apart, slowly building larger worlds. The environment of the disk determined what materials could survive. Close to the young sun, temperatures were high, allowing only metals and rocky compounds to remain solid. This is why the inner solar system formed small, dense planets like Mercury, Venus, Earth, and Mars. Farther out, beyond what is often called the frost line, temperatures dropped enough for water, methane, and ammonia to freeze. Ice added mass to growing cores, allowing them to become large enough to capture vast envelopes of hydrogen and helium, eventually forming the giant planets. The architecture of the solar system, with rocky planets inside and gas and ice giants outside, emerged from this temperature gradient in the early disk. The process did not end once planets formed. Gravitational interactions among the giant planets likely caused them to migrate from their original positions. Jupiter may have moved inward before shifting outward again, while Saturn, Uranus, and Neptune migrated farther from the Sun. These movements scattered leftover debris throughout the system, shaping the asteroid belt, populating the Kuiper belt, and sending countless icy bodies into the distant Oort cloud. During this chaotic era, the inner planets experienced heavy bombardment from asteroids and comets. These impacts may have delivered water and organic compounds to Earth, contributing to the ingredients necessary for life. The early solar system was not stable or quiet. It was dynamic and violent, with collisions and rearrangements shaping the worlds we see today. Earth's habitability emerged from a combination of location and circumstance, positioned about 1 astronomical unit from the Sun. Earth lies within the region where temperatures allow liquid water to exist on the surface. This habitable zone is not a guarantee of life, but it provides the basic thermal conditions needed for stable oceans. Venus, slightly closer to the Sun, experienced runaway greenhouse warming that evaporated any early water, while Mars, farther out and smaller, could not retain a thick atmosphere and cooled into a cold, dry world. Earth's distance alone, however, is only part of the explanation. Its size allowed it to maintain a substantial atmosphere and long-term geological activity. Plate tectonics recycle carbon between the atmosphere and interior, helping regulate climate over geological timescales. Another crucial factor was the formation of the Moon. Early in Earth's history, a Mars-sized object likely collided with the young planet, ejecting debris that eventually coalesced into the Moon. This event altered Earth's rotation and stabilized its axial tilt, reducing long-term climate instability. The Moon also generates tides, which may have influenced early chemical cycles along coastlines. Earth's molten core, rich in iron, generates a magnetic field that shields the planet from solar wind, preventing atmospheric erosion, combined with an atmosphere composed largely of nitrogen and oxygen, and abundant surface water covering about 70% of the planet. These conditions created an environment capable of supporting complex chemistry and eventually life. The result was not predetermined. Slight changes in distance, mass, or early collisions could have produced a very different world. Instead, Earth formed within a narrow set of parameters shaped by the physics of the early solar nebula and the chaotic evolution that followed. Among the many bodies that emerged from the same disk, one planet developed stable oceans, a protective atmosphere, and long-term geological activity, turning a common outcome of planet formation into an environment capable of sustaining life over billions of years. After tracing the structure of the solar system from the sun to its distant outskirts, the perspective shifts naturally toward time because scale in space only becomes meaningful when placed alongside scale in duration. The universe is about 8 billion years old. Our planet formed roughly 5 billion years ago, meaning that for most of cosmic history, neither Earth nor the solar system existed. For billions of years, stars formed and died. Galaxies evolved, and heavy elements accumulated before the conditions necessary for rocky planets and complex chemistry appeared. Life on Earth emerged relatively quickly once the planet cooled, but even then, it remained simple for most of its existence. Single-celled organisms dominated for billions of years, gradually transforming the atmosphere and oceans before complex life arose only within the last few 100 million years. Humans arrived extraordinarily late, with anatomically modern Homo sapiens appearing about 300,000 years ago, a moment so brief compared with Earth's age that it resembles a thin line at the very end of a long timeline. Within that short interval, human history occupies an even smaller portion. Agriculture began around 10,000 years ago, writing around 5,000 years ago, and modern science only a few centuries ago. Space exploration belongs to the last few decades. Yet in that time, humanity has extended its presence beyond Earth, landing on the moon, sending probes to every major planet, and dispatching spacecraft that have crossed into interstellar space. Voyager 1 and Voyager 2, launched in 1977, now travel beyond the heliosphere, carrying with them golden records containing sounds, images, and greetings from Earth. These spacecraft move slowly compared to cosmic distances, yet they will drift through the galaxy for millions or billions of years, long after Earth itself changes beyond recognition. Their trajectories do not aim at specific stars, but instead trace a quiet outward motion, symbolic of exploration without expectation of return. This expansion of awareness also reshaped our understanding of place. The solar system is only one structure within the Milky Way, a galaxy containing hundreds of billions of stars. The Milky Way itself is one among trillions of galaxies spread across the observable universe. Each step outward reduces the apparent significance of any single world, including Earth, yet it also reveals something unexpected. Within this immense setting, one small planet developed conditions stable enough for life to emerge and evolve into conscious observers, capable of understanding the larger structure. The same physics that formed stars and planets also allowed chemistry to organize into biology and eventually into intelligence, able to measure distances, analyze spectra, and reconstruct cosmic history. The future stretches far beyond human time scales. The sun will gradually brighten over billions of years, eventually expanding into a red giant and transforming the inner solar system. Long before that, Earth's surface conditions will change as increasing solar luminosity alters climate and oceans. On much longer time scales, the galaxy itself will evolve, merging with neighboring galaxies and redistributing stars and planetary systems. Even these events occur within a universe that continues expanding, gradually thinning matter and energy across unimaginable spans of time. Compared with such durations, human existence is brief, yet the ability to observe and interpret these processes compresses vast scales into comprehension. Exploration, both robotic and observational, extends this understanding. Missions to Mars analyze ancient environments that may once have supported water. Space telescopes detect planets around distant stars. some orbiting within regions where liquid water might exist, future instruments may identify atmospheric signatures indicating biological activity beyond Earth. These efforts do not alter the scale of the universe, but they change how it is perceived, turning distant points of light into potential worlds with their own histories. The solar system, once imagined as isolated, becomes one example among many, while Earth remains the only known place where life has developed into self-awareness. Placed against this background, humanity occupies a narrow interval in both space and time. Yet it represents a phase in which matter becomes capable of reflection. The distances remain vast, the durations immense, and the structures largely indifferent to observation. But within one orbit, around an ordinary star, a species emerged that can trace its origins to a collapsing cloud of gas and dust and project its understanding outward across billions of kilometers and billions of years, connecting local experience with cosmic context